Assalamualaikum and a very good day to my panels, Dr. Amiruddin and Dr. Mumtaz, my supervisors, Associate Professor Dr. Siti Hafiza and Associate Professor Dr. Nur Badro. Today, I will present my research title towards autonomous scalable link prediction application in social networks. As we all know, existing social networks platform each has its own specialty delivered to its user. For example, people sign up to Facebook to share posts with friends and reach more all connections. People sign up to Twitter for faster news and viral stories. People sign up to Instagram to share everyday moments to their connection. And as illustrated in the bar graph, almost 3.8 billion people were active internet users as of April 2020, reported by Statista, and is estimated to continue increasing linearly. So, link prediction is one of the most significant ways to better understand how interactions and connections between the individuals in social networks platform evolving over time. Prevailing link prediction approaches prove their significance of applying in social network, such as to predict future friends' connection, or to infer social interactions between two connected friends, and then to recommend new friends, and also to detect unwanted connection like the spammers, the fake users exist in the network. However, existing single computing approaches for link prediction fail to provide a good performance that is scaled to massive data. Therefore, Zhu et al. Have proposed a distributed computing environment to overcome the single computing problem to provide a scalable link prediction performance in massive data. And they have successfully proved improvement on the prediction execution time, that they are able to execute more than 1 gigabyte of data in 220 seconds only. So to provide you an overview about scalable and distributed computing environment, the problem is actually broken into discrete parts that can be solved concurrently, and then each part is further broken down to a series of instructions. And this instruction from each part executed is simultaneously on different processors, meaning we use more than one computer, and that the problem is able to solve in less time with multiple compute resources that we set up. I have done a comprehensive literature review in my previous semester, which this is the taxonomy. I divided link prediction into 4 categories, which is based on need measure, based on the approaches, applications, and also the social networks context. And to highlight the approaches, there are 4 categories: algorithmic, similarity, hybrid, and probabilistic. And majority of them actually propose algorithmic, that is categorized into meta-heuristic, metric factorization, and machine learning. And also majority of them also using similarity, which is using local, global, or quasi-local indices. This table 1 shows comparison of 5 related works that are the most relevant to my research area. They are CBRA, PCLP, PSPLPA, DPM, and DTPLP. I compare them by their application, networks, social network context, approaches, program model, topological properties, and limitation. But then I want to highlight the programming model. Programming model refer to the style of programming where execution is invoked. As you can see from the table, from these 5 related works, one of them use MapReduce in Hadoop, and then 3 works use Pregel model in GraphX, and one of them use distribution partition merge (DPM). They are actually different for MapReduce and Pregel on how they breaks our code into a set of tasks and run it concurrently. So the explanation of these 2 programming models are detailed in my report. Let's see the limitation of each works. So the first one, CBRA, they say that MapReduce does not allow read nodes and edges information and that they are not suitable for graph processing. And then for PCLP, they said that the parallel programming involves a lot of message generation and transfer, which can affect the system performance and also actually can affect the efficiency of scalable link prediction, which we will show. This is actually our research gap. And for PSPLPA, they said that the calculation of similarity can be enhanced to get more stable result. Also can improve the approach by implementing it in dynamic network. So basically this is in terms of accuracy, but we will not focus on this. And DPM has high memory consumption compared to fork join in case of path-based link prediction approach. This is also in terms of memory consumption, but we won't focus to DPM because DPM is using a custom programming model, so it's limited to us. And then for the TPLP, it said that the performance of the algorithm in social network is low. The algorithm better at predicting dynamic interaction rather than existing social relations. This is because they are focusing to dynamic social networks, so there's still room for improvement to their work. So the table 2 also highlighted the 5 related works as in the table 1, but then I compare them by their form of data, size of data, by their infrastructure, how many core they use, how many memory they set, and also how big are the cluster, and also what is the algorithm that they use, the evaluation matrix, and also the benchmark. And for algorithm, CBRA use clustering-based RA index algorithm, which we will adapt in our analysis and experiment as power iteration clustering application. And then PCLP, PSPLPA, and DTPLP using the same algorithm, which is parallel label propagation algorithm, that we also adapt in our analysis and experiment as label propagation algorithm. And also DPM use path-based algorithm, which is based on local path and cars. But then for our experiment, we will pick only 3 applications which use these 2 algorithms, which is the clustering, the parallel label propagation algorithm, and the third one is the map reduce itself, because we want to show the performance and efficiency of each of these 3 different applications. To state the problem of our research area based on the current scalable link prediction that we highlight previously, so we can say that parallel programming involves lots of message transfer and generation that may cause communication overhead, and this affect the execution time performance of the scalable link prediction. Furthermore, in the matter of social networks data, they are skewed in distribution that lead to uneven data distribution. This actually happens during data partitioning process before prediction in distributed nodes begin. Also, an uneven data distribution can cause inefficient resource utilization. For example, each distributed nodes utilize different amount of time and also different amount of memory usage. And this actually have negatively compromised the execution of scalable link prediction in social networks, because we all know that scalable or parallel computing should be balanced between their distributed nodes. Hence, our research attempt to model an autonomous scalable framework for efficient link prediction in massive social networks. We want to improve not only the performance but also the quality of the prediction with adequate and best possible use of resources without excess hardware setup. So to expand our research aim, this is our research objective mapped to research question and research outcome. So the research objective first is to analyze existing approaches and applications of link prediction in social networks, and the second is to assess the scalability of prevailing scalable link prediction application using different size of data and workload. And then the third one is to develop a novel scalable framework for an efficient link prediction in social network, and the last objective is to evaluate the performance and efficiency of the new proposed scalable framework for efficient link prediction and then compare it with existing study. So for the question, the first one is, what are the various approaches and applications of link prediction in social networks domain? These the findings on existing approaches and applications of link prediction in social networks are published in my review paper. And then the second question is, what is the effect on scalability of different data and workload when the proposed algorithm performs link prediction tasks? This one is we will produce from experiment which we will have novel findings on the scalability of proposed algorithm when performing link prediction. And then the third question is, how can a novel scalable framework be developed to perform link prediction with scalability for large Twitter social networks? The outcome is integrated framework in Spark distributed framework for scalable and efficient link prediction. And the last question is, what level of performance improvement has the proposed framework achieved when compared with existing solution? The outcome will be result of performance comparison with existing approaches. For research scope, I focus link prediction analysis in social network, in scalability issue using algorithmic approach, and in distributed computing, focusing on resource inefficiency and excessive communication time. So for our research methodology, we use design science research methodology as illustrated in this figure 2 to analyze the effectiveness of existing scalable link prediction on top of Spark and Hadoop MapReduce. So firstly, we identifying problem and motivation based on in systematic literature review, and then we define objective of a solution by constructing experiment objective and research question, and then we perform design and development. And then for the demonstration, we illustrate experiment result in the report. And for evaluation, we consider performance and resource utilization of the application. And lastly, for communication, we report the findings. Moving on to analysis and experiment, we define objective for a solution. So this is the research objective and research question. The first one is to analyze the effectiveness of scalable link prediction application on top of Apache Spark and Hadoop MapReduce framework. And then the second objective is to differentiate two widely used programming model for scalable link prediction that are MapReduce and Parallel. And the third objective is to investigate the correlations of three variety of scalable link prediction in three different applications, which is the PIC, LPA, and MR. Okay, for design and development of the experiment, we have 4 phases. Firstly, we collect the Twitter data via Twitter API and store the raw data in local DB. And then phase 2, data processing, we process the data into the form of graph, which is edge list. And then the phase 3 is application deployment, where we develop and replicate 3 link prediction application adapted from related works, which is the PIC, LPA, and MR. And then we deploy the 3 in Spark server environment. And lastly, in phase 4, we execute the application using automated script in the Spark framework. So to summarize the analysis and experiment result, I will answer each research question. To answer the first research question, we have experimentally compared 3 prevailing scalable link prediction, PIC, LPA, and MR, in Spark utilizing 2 different graph model, which is MapReduce and Parallel. And then we evaluate them by the execution time, success rate, data shuffling, resource utilization such as CPU, memory, disk, and network. And to conclude, previous reported result hold true in terms of the execution time and their scalability perspective. For question number 2, we observe that partitioning increases the performance efficiency of link prediction application. The higher number of partitions set, the higher scalability performance of application. However, it actually highly dependent on the data nature that we use. And furthermore, we observe that partitioning increment is highly effective when data is especially at larger scale. When at smaller scale, the total execution time does not reduce as much as at the larger scale. So the question is, how do we set the partitioning number optimally depending on the data size before the application execution? For research question number 3, we found out that given variety of data size, each application has performance drops at different level. For example, PIC has performance drops at 500,000 data size, and for LPA, they have 0 failure rate. For MapReduce, they have inconsistent failure rate and success rate. You can see in my graph in the report. And so to conclude, application performance is actually depend on their requirements, such as the memory, parallelization method, the network, and also the input output. And for the research question number 4, we conclude that both models, the Parallel and MapReduce, suits large-scale data processing in terms of the efficiency and iterative computation of graph data. but only Prager can complete the task, the implementation task with 100% success rate. For MapReduce, they have inconsistent rate. However, when the resource such as memory is not enough, the performance of Prager can drop and be worse than MapReduce. For example, for both PIC and label propagation algorithm LPA, we observe that the success rate and failure is manageable by tuning the configuration of Spark setup optimally, meaning that we set memory and cores to use optimally. And this shows the efficiency of Prager are actually highly dependent on the application settings of configuration, not only based on the data size. Moving on to proposed solution, I will explain what is autonomic computing. It's a system that can adapt to changes triggered by a change in the system's own state or the state of its environment. In 2001, IBM presents a reference model named MapK Autonomic Loop. This MapK loop over monitor, analyze, plan, execute, and knowledge, such as illustrated in figure besides. And then correspondingly, an autonomic system requires sensor to sense changes in the managing element. The managing element can be web servers, cloud servers, or cluster, but in my case, is the master node in Spark framework. As the changes detected, effectors act as reaction mechanism to respond to the changes, and then a decision-making engine is an autonomic manager take place to make the correct assessment. Also, autonomic system carries some properties, for example, self-configuring, self-healing, self-optimizing, and self-protecting. So for my proposed solution, I want to use self-configuring and self-optimizing. For our proposed solution, we have two big aim, which the first one is optimize partitioning, where we will improvise current vertex card partitioning implemented in Spark GraphX, and then we will simplify complexity so it won't affect the whole application performance and efficiency except to make the input data distribution balance. And then the second aim is autonomic computing for self-optimizer and self-configure, where this one is responsible for configuration before Spark submits the application. Because in previous experiment, we allocate manually the configuration of executor core, memory, and data locality. But in our SOSC framework, we propose to check and predict the application, then automatically tune the configuration before Spark submit the application to distributed nodes. Okay, the figure 4 actually show full architecture of our proposed framework SOSC, and integrated with Apache Spark cluster, since Apache Spark is an open source. So we figure out that we can adapt the MapK loop, which is from the autonomic computing concept, to this Spark cluster. So in our SOSC framework, we will have three modules, which is collect, decision making, and update. Collect will have read data size, read at complexity, read memory usage. And then decision making, we have inspect partition method, check executor memory, check executor core, and examine locality. And for update, we will have declare partition method, declare executor memory, declare executor core, declare data shuffling. And all of these method in the module will be later updated by the time I'll develop the framework. In decision making module, we will use neural network based model, where the neural network based model will have three layers, which is convolutional layers, fully connected layer, and also the output class. Neural network will undergo training of the data that we have read from collect module, which is the application configuration, and then this neural network model will output an optimal application configuration and update to the update module. Moving on to proposed evaluation, we want to in terms of performance, we plan to compare with TSH and SCID. This is the related work that I highlight in my report. And in terms of efficiency, I plan to measure workload results and compare them with existing work. The M80 and 2-month auto-tuning framework also highlighted in my report. And in addition, we further conduct an experiment to measure algorithm scalability using varying size of data sets while keeping a fixed cluster size of 4 nodes, and we want to maintain our low cost cluster setup. Table 8 shows my research schedule. In proposal presentation previously, I have highlighted my research gap from existing scalable in prediction work, and then referring to the research schedule, I am at the evaluate existing module and propose new model. So for confirmation presentation, I proved the research gap thoroughly through experimenting with the existing scalable in prediction work, and then presents the finding outcome of the evaluation. And from here I also present my proposed solution that solve the proven research gap. For my next candidature presentation, I plan to present half of my working proposed solution and the findings at that time. So that's all from me. Thank you.